So we're here at a conference about the physics of events, but also the physics of observers. So if you think about classical physics, the role of the observer there isn't really important, because the idea is that things happen independently of who's looking at them, and you don't really need to think of the role of an observer.
Exactly.
So how is that different in quantum mechanics, for example? Why does the observer play a special role there?
Well, here's what's going on. So quantum mechanics says, or seems to say, if you take it literally, that particles can be in two places at once or going at two speeds at once. And it also seems to say that when you make a measurement of a quantum system, or more generally take the word measurement out, whenever some dynamical interaction causes small-scale effects to be magnified up to large-scale effects, whether that's a measurement or a cosmic ray causing mutation in your body or just the flickering of a broken fluorescent light bulb, any of those phenomena mean that what the mathematics of the theory says is that the macro world is doing two things at the same time. So, three options to deal with that. One is change the equations, but we've said that's kind of difficult. Another is to say it's the observer that ensures that one thing happens rather than another. So it's the point of observation where we stop using the description that says two things are happening at the same time and move to using a description where only one thing happens. And so the observer plays a crucial role. And the third thing we can do is to say we should never make that move. We should just accept the fact that what the theory says, that two things are happening at the same time, really is what's going on. Hence your choices: change the physics, fundamental role for the observer, or many worlds.
And you said that you tend towards the idea that let's leave the observer out of it and go towards the many worlds interpretation.
I think that last move is the right thing to do, and I think one reason to think that is because observers are just physical systems, and it doesn't really make sense for us not to be able to just apply the laws of physics to observers, just like in classical mechanics. But I think anyone who accepts that way of thinking about quantum mechanics will recognise that it's quite crazy sounding, and you can see the price one pays for an observer-independent physics.
Would you reject, because I just spoke to David Wallace, for example, who said his way sort of around the measurement and observer mystery is to go for the many worlds interpretation, which just to say it quickly, which basically says that when you do make your measurement and there are different possible outcomes, then, well, the world just splits into different branches where in each of which you see one of the outcomes. So is that something that you would not necessarily go with then?
It's not my favourite way of thinking about quantum theory for several reasons. First, the picture you just described, although it's very weird and bizarre, in a sense still sounds rather simple. When you try and push people on the technical details of how that picture actually emerges, what they mean by the wave function splitting, you suddenly find that people who you thought agreed with each other and all were many worlders don't agree with each other at all. It's not literally true that everybody has their own proposal, but there are lots and lots of different proposals, and they're inconsistent with each other, and they all have problems. There's been a lot of interesting work, and I think a lot of progress in understanding ways of understanding more directly the mathematics of quantum theory. Not in the same way that we understand classical mechanics. It's a very different theory, and it's a much less intuitive theory for us because it describes a world that we only experience indirectly. But in something like the same way, in that we have a clearer picture of how you map from the mathematics to what's going on in reality, what's going on in the physics, whether or not there's an observer or a measurement taking place. So there are some radically different lines of thought out there on that. My own favourite would be following ideas that John Bell, who was one of the deepest thinkers of the last century about quantum theory in particular, first set out and made the case for, which is that you need to supplement the quantum wave function by some extra variables. People sometimes use the term hidden variables. I agree with John Bell, it's exactly the wrong term, because these extra variables...
Just to interrupt quickly, so the quantum wave function is the mathematical object that describes a particular state.
Yeah.
And you're suggesting that there has to be an extra sort of axiom, is it, or an extra something in the theory that brings it together with our classical experience that kind of reconciles it?
More than that, I think and this is very controversial, and I think I'm in the minority, but it's a respectable minority. But there has to be extra mathematical structure beyond the wave function. Certainly, when you're talking about the quantum theory of the universe, and even for me, this isn't a dogma. It seems to be the most promising line of thought, and it's certainly leading in an interesting direction. So it's my hunch.